So we're in your chemistry book, section 3, and we're going to go on with nuclear reactions. And so I'm going to divide this into 2 parts because it gets kind of in depth and you need to understand. So, well, let's start with chemical reactions. We talked about chemical reactions in the last chapter, and chemical reactions are described, as having chemical equations, right? Well, nuclear reactions are described and have nuclear equations. And you can see right here how the nuclear equation is different than the different chemicals are reacting with each other. Now we have what's reacting in the nucleus. So they're called nuclear reactions. Here's an example. We have 8 protons, and the protons with the atomic weight to the positive proton, 1 to 1, and onto the 8 neutrons is the weight 1 to 0, no charge there. And then we have the electron is 8 with no weight, has no weight, but it has a negative charge. And you add these all up and you get 16 over 8 with oxygen, plus again, remember we talked in the last section about energy. So we're working with nuclear equations. You have to keep in mind that nuclear reactions that shall follow 2 important rules. And what are these rules? These rules we have to know, and it comes from the conservation of energy and mass, right? The mass number must be conserved. The sum of the mass number must equal the sum of the mass number on both sides of equations, right? So that we know the mass number is always, these masses are always going to be conserved. The other is the nuclear charge, that bottom number is charged, the charge number, the nuclear charge or the atomic number charge must be conserved too. So the sum of the charges must be equal on both sides of the equations. So we need to know that. Those are the 2 rules. Just know the conservation, so that when you're talking about an equation like that, you know when you add these up, it's going to have to equal the same on this side as the same on this side, right? When you have the mass number and the nuclear charge or the atomic number. The atomic number is the positive charge. Remember, the positive or negative charge is the atomic number. So now we're going to see the types of nuclear decay. These are pretty amazing because it's kind of practical and what you're gonna see and what harm radiation can do too in the midst of this. So let's talk about whenever atomic nucleus breaks up or changes, it emits radiation, and it's said to undergo nuclear decay or radioactive decay. And they found, okay, this radiation is not the same. This that it's different in some places. So they basically found out there's different types. And they put these into first 2 main types. And the 2 main types are alpha decay and beta decay. And either type of decay may also involve the emission of high energy electromagnetic waves called gamma waves. And some other types of nuclear reaction may also involve the emission of high speed neutrons, which are called neutron radiation. So there's 4 different things we need to be aware of. 2 different types of decay, alpha decay and beta decay. And with these decays, you're going to have electromagnetic gamma rays, and you're also, if neutrons are shot from the nuclear, basically neutrons are traveling and bumping into other neutrons like we have in fission, when you have, which we're actually showed us, the nuclear bomb in the midst of that. But this is another type of high-speed neutrons traveling, which is related to radioactive decay. These 4 things, these 2 we're going to talk about first. So alpha decay, and here's the sign for alpha. It's like a Greek A. So alpha decay occurs when we'll go up here a little bit here. Alpha decay when occurs when an unstable atom ejects a clump. And this clump, what's this clump that it ejects? It has 2 protons and 2 neutrons in this clump. And they call this clump an alpha particle. So 2 protons and 2 neutrons are called an alpha particle. And so they're just getting rid of a particle, especially when you have a really heavy, nucleuses and these heavy atoms like uranium, and you have these alpha particles are shot off, or an alpha particle because it wants to be stable, so it's going to shoot off this particle. And so this particle, the alpha particle, emitting this radioactive decay. The atom becomes 2 less. So you're going to subtract 2 less atomic number. The atom number or atomic number becomes 2 less. And the atom's weight becomes 4 less, because what's it shooting? It's getting rid of 2 protons and 2 neutrons. That's 4 particles it's getting rid of from the nucleus, 2 and 2. And 2 of them are the atomic number that are positive, and 2 of them are neutral. So it says, for example, if an atom of uranium ejects an alpha particle, it becomes an atom of thorium with atomic number 90. So it's getting rid of 2. So you're getting rid of 2 protons because it's changing the atomic number. And then the alpha particle actually has 2 positive ions of helium, -4. So it looks like a helium. So this alpha particle, if you say, what does the alpha particle look like? It looks like a helium, because it's taking off 4 particles from the nucleus, which 2 of them are protons and 2 of them are neutrons. And if you look at that, it looks like a helium. So a lot of times an alpha particle will be related to helium, because helium, if you look on your periodic chart, helium has that. It has +2 particles of or 2 protons, and then 2 neutrons. We're just talking about the 2 neutrons. Also, it's positively attracted to the negative change plate. So let's look at that change plate thing. They're talking about change plate. Let's look over here. Here's the change plate. You see how if an alpha particle taking out, it's because an alpha particle is positive, it's going to want to go to the negative charge plate, or the negative side of the charge. So it's going to go up, and it's going to go towards the negative charge plate. Now, if you have the opposite, when you have a beta ray that's a negative charge, it's going to go the opposite way. Just to know what they're talking about when they say that the charge field or charge, that's the charge plate. So let's go back to the alpha. So alphas, okay? The atomic number becomes 2 less, and then the atomic weight becomes 4 less, which is just like a helium. And it's the most common form. And as you see, basically the alpha, as we see the alpha down here, alpha decay, here's of uranium. So here we have uranium, 238, which is pretty amazing, and 92. So 238 is the atomic number, and then 92 is that positive charge, protons. And so it's going to emit a helium or an alpha particle, which is weight is 4. There's 2 and 2 protons and 2 neutrons, and its atomic number, or its positive number, which is protons, would be 2. And so here we have, it's changed to 234, because you minus 238 to 4, you get 234. And then it's going to change, get rid of that 2, you're going to get 90, so you have 234, and it changed into a whole new molecule here. So in the midst of this, you see how now it's thorium. It's a whole new, it has split off an alpha particle. So the alpha particle here is considered the alpha particle, the atomic number is A. Z is this bottom number, which is the positive proton, right? So just to read that equation, we have to look the rules. Mass number is conserved. 238 equals 4 plus 234 up here. And the atomic number, nuclear charge, is conserved. So 92 on this side, 92 on this side. So just make sure both sides equal each other. Okay, this little section just says this alpha emitter called americium, americium 241. Americium is actually in smoke detectors, of all things. The alpha particles from the decay, they ionize in the air, forming those ions, right? As the alpha particles are turning positive, you have a different electrolytes, or not electrolytes, electrical charge in the air. And so the alpha particles from the decaying americium ionize into nearby molecules, allowing a small electric current to flow through the two electrodes. So in the midst of the smoke detector, you have these electrodes flowing and giving off this positive charge with alpha particles. So when a smoke comes in, it decreases this current because the smoke gets in the way, right? Because alpha particles are big and it gets in the way of them. And so this causes the smoke detector to go off. Kind of neat. They use alpha particles. One thing we know, they use alpha particles in a smoke detector. So beta decay. That's the other type of decay, beta. Remember, we have alpha, and then we have beta. And beta decay happens. And first of all, you need to know the sign. It's the Greek sign of B, beta. So beta decay, the neutrons in the nucleus change into protons. So one neutron, actually. So what happens, you have a very heavy, probably have a very heavy nucleus of a heavy element. And then so it's so heavy that some of the neutrons end up changing into protons. And when they do change into a proton, the electrons become unstable because the charge is too positive, and so then it would emit this electron. So it's different from electricity when we talked about electrons being emitted as ions. Now we look and we see, okay, basically we have a neutron that's turning into a proton. It's getting a charge. And when it gets this charge, then the electron electron in the outer shell decides to take off. So basically you need to know about beta decay is an electron is going to take off because a neutron turned into a proton. So this electron is emitted from the nucleus called beta particle. And it's identical to any other electron, only its origin differs, because the reason it takes off is because a neutron turned into a proton, right? But otherwise it looks just like an electron. It's electron in fact. So beta particles are symbolized like this with a 0. That means they weigh nothing, comparatively so light, 0, and a negative 1. So whenever you see an electron like that with a 0, -1 like this, that means, or this means, here's a beta. They can use it as a beta or electron, E meaning electron. So they can say it as electron, or they can say beta is electron. So that's just how you're going to see it in a formula. It's those two ways. So, and of course, beta particles are so light. They're like 0.00055 units compared to the very heavy proton and alphas. The alphas are very heavy. And because they're negative charged, they're going to be attracted to the positive plate, and the electric field is around it. So there's electric field around here. There's one plate on one side that is going to be charged positive. So electrons are going to, of course, be drawn over to the positive, because like charges repel and unlike, so it's going to go to the negative electron will go to the positive, just as the alpha went over to the negative because it's positive. Just remember, alpha rays are positive. Alpha, number 1, positive rays, and beta are negative rays, so, and this is the radio radioactive material. Here's the shield, and you can see as they come out, the beta rays are going to go over to the positive side, right? And then the alpha rays are going to go over to the negative side. So let's see here if I covered all this beta stuff here. So whenever you can always know a beta equation here. Here's one too. Why? Because it's going to look like this. You'll see 14, 6. And 14. So this is this nucleus has 7 protons and 7 neutrons, making it as nitrogen. So first of all, we have carbon. So carbon has 6. 6 is its atomic number, right? And so it has 6 and it has 14. So what's that mean? It's going to have 7 neutrons and 6. Yeah, or I'm sorry, 8. Well, anyway, it's 14 has 6 protons and 8 neutrons. That's what I'm talking about. It's 14, and so 6 is going to be its protons. Well, what happens is that one of these neutrons in the 14 is one of these neutrons will want to change into, it's going to change into a proton, which the weight doesn't change, so it's still going to be 14, but it's going to have a charge on it, so this number is going to turn to 7. So whenever you see this bottom number turning to 1 difference, you're going to know it's going to be beta, so as and then you're going to see this is the electron. Because this happened, it's going to put off an electron. It's going to send off an electron ray in the midst. Okay? And bromine is another one. Here's bromine, and it's decaying into krypton. How does it decay? Bromine's, the atomic weight stays the same because it has neutrons and protons the same, but one neutron here, one of these 82 neutrons, is going to change into a proton, making the atomic charge positive, making the atomic protons more because it's changing into protons. And then again, it's going to shoot off an extra electron so that it can become neutral. So that's the beta emission. So I hope you got that. Beta decay. So let's go on. Both the mass number and the atomic number are always conserved. So we know that. They're going to give you another example here, and it's the beta emitter. Hydrogen 3 is commonly used in, basically what they want to tell you here is how do we use these beta rays, Okay, we see these beta rays, but can they be used for anything? Well, yes. Here's the application of a beta decay, where the beta emitter hydrogen 3 is commonly used in self-luminous watches and firearm sights and exit signs. So basically, this luminous nature would be emitted in the midst of beta decay. And here's some examples in the watches, in the watch there. So, okay, let's go on. Just to know this is an example of beta rays. So the other thing, okay, when we talk about gamma rays are not from the nucleus. We don't have the nucleus really, in the midst of gamma rays shooting particles like we did with the other two. But gamma radiation happens because usually it happens with either alpha or beta decay radiation, or I should say radiation, but the gamma radiation happens too. But gamma radiation, here's the Greek symbol. It looks like a Y, that's the symbol. I think you might need to know that. Gamma, that means gamma. Gamma radiation are electromagnetic waves of very high frequency and energy. We know them on the electromagnetic scale, don't we? And gamma decay often occurs in a nucleus that have just gone over alpha or beta. So you have this nucleus, it's gone through this huge process now, and now it's going to be emitting more energy in these gamma decay rays, or gamma rays. So gamma rays are uncharged. They don't have any charges. Here's a picture here. If you have gamma rays, here's gamma rays. They just go straight up. They don't go either way. They're not charged at all. Gamma rays are just, and they occur in the nucleus that have just undergone this other process of alpha or beta. And they're in an excited state, the gamma rays. So since these rays carry no charge, they do not have any identity in the nucleus either. So example would be cobalt-60 that's used to treat cancer. Gamma rays are treated cancer. They have, there's a beta decay with strong gamma rays coming out, and they direct these gamma rays at the tumors of cancer. And so they try to, that's when you say radiation therapy, and a lot of times they use gamma rays, and they direct these gamma rays at tumors, cancer tumors, to get rid of them, right? Because gamma rays are very strong rays, electromagnetic waves, very strong, so, and in a very excited state. So on to the last here, gamma rays. Here's a picture with it treating cancer with gamma rays, how important that. So let's go on to here. Well, this chart here tells about it. So you have alpha decay, too heavy, Z is too high, not enough neutrons. Okay, anyway, cause of reaction is you have a very heavy weight to get rid of, and so you're going to decrease. The Z is the atomic number, so you're going to decrease, decrease 2 protons, and you're going to change the mass with 2 neutrons. So you're going to decrease the mass by 4 with 2 neutrons and 2 protons counted, and then the N to Z will be increased, and this is example of one. You just basically have this alpha particle. So it looks like, here they wrote down helium. It looks like a helium particle, so they called it helium. So this is the alpha particle. It's Cm is turning into plutonium here. You have the helium given off. Beta decay, you have too many neutrons, so a neutron is turning to a proton, and when it turns to a proton, basically that turning to a proton increases basically the charge, but the charge will emit an radiation of an electron right here. So here we have the electron taking off. The same with and then actually gamma, I shouldn't say the same way, the gamma rays happen in the midst of one of these two happening. The nucleus is in an excited state. There's no change of anything, but actually just a ray is shot off, and it looks like a gamma ray. Nothing changes inside the nucleus with gamma rays. It's just the energy that's from the gamma ray. Okay. Neutron radiation. What is neutron radiation? Okay, neutron radiation is different. Now we had the alpha particle radiation, we have the beta particle radiation, we have the gamma rays radiation. Now we have the neutron radiation. This is pretty rare because ordinarily nuclear decay produces either alpha or beta particles and gamma rays. But some types, and a lot of these types, they're going to study where they shoot neutrons, cause neutrons to be ejected from the nucleus altogether. It's shooting neutrons, bombarding neutrons. And this bombardment of neutrons is called neutron radiation. And so the nucleus is affected, and neutrons are not affected by electromagnetic fields because they have neutrons are neutral. They have no charge on them. So when they're shot off, they're not affected by the electromagnetic fields. And neutrons can actually pass through almost anything, many types of matter. So when you have neutron rays, you have to have huge, deflectors. Like they'll pass through a lot of different things. So you're going to have to put like concrete walls and tons and everything to get the neutrons. It takes a lot because neutrons can pass through a lot. And they're deflected or absorbed only when they collide with an atomic nucleus. So these neutrons are shot off and they're going to keep going and going. Then suddenly they're going to bump into another nucleus, and then they're going to deflect. When they deflect, then that nucleus will split and go into the next one, and the next one. This is called fission. This is nucleus splitting by these neutron radiation. So the chief use of neutron radiation is the production of transuranium elements. So elements with atomic numbers beyond uranium. So if they have very heavy, then the neutron coming loose is going to be more common. The element plutonium, and these are used in nuclear reactors and bombs as well, and nuclear weapons, was produced by a reaction between a neutron radiation and a uranium. They took uranium and basically in the midst of all this, they produced these flying neutrons. They would bombard, and in the midst of that, a lot of energy tons of energy releases into like a bomb. So, but like gamma rays, neutron beams can also be used in the treatment of cancer, of destroying those cancer tumors. So let's do these problems here. I think we'll do the problems, and then we'll do the problems in a little bit, and then we'll stop in just a bit. So, identify the missing particle in each of the following nuclear things. So, this first one. So it's going to tell you how to do this. Let me just show you how to do this here. So if you have RF, this is a heavy, unusual, element here. With 257 is going to be the atomic number of protons and neutrons. And then you have 104, that's going to be the protons or the positive charge. Well, it looks like the positive charge decreases by 2 to make NO, which makes a new element. But the top number decreases by 4. Oh, brother. So what are you going to say? What are you going to put there? You know for sure that that's going to be an alpha particle. And what does an alpha particle look like? It looks like helium. So let's see if we got that right. The alpha particle looks like it's alpha decay. And it looks like 4, 2, or helium. Or 4, you can say helium or alpha, 4 over 2. See? Okay, we did that one. Let's go on to the next one. So we have 43 is the weight, atomic, with neutrons and protons. Then we have 19. This is protons or positive charge. And here we have, it stays 43. So we have no change here. But look, we have actually one of these neutrons turned into a proton. So this is going to emit an electron charge. So let's see how they write that. So here we have, and of course emitting electric charge is going to be beta decay when they turn. So here you have this, and the particle has no mass change, and a negative is the electron. So you're going to write it as 0 over 1 negative electron, or you can use it as beta or electron, however you want. But anyway, here's what you're going to write it as. So let's go on to the next one. So we have another geranium, I think. Geranium, I'm pronouncing that right. But 78 atomic number, 32, or 78 atomic mass, neutrons and protons. 32 atomic number would be protons. And now what you're going to just get rid of now you're getting rid of an electron. So if you're getting rid of electron, that means that one of these neutrons has to turn into a proton. So you can know it's going to be 78. The 78 is not going to change, but this 32 is going to change as this is going to get higher, really, because a neutron is going to turn into it. See if we got that right. So, where was that? Which one were we at here? The particle is electron, so the reaction is example of beta decay. Let's see if did we do that wrong or right? Let's see. Oh, the particle is electron. Yeah, that's what this is when a neutron turns into a proton, it emits electron, and this is beta decay. So we were right. So basically that particle is electron, so the reaction is beta decay. And so you are going to have the 78 is going to stay the same. Thus, it's going to turn into a new particle. So, but they have the particle. You have to look on the periodic table and find out what particle this is, and you'll find out it's 78 over 33, which we knew is AS. So we'd have to look that up on the table. So basically, you have this, and this is going to change as you use electron. 1 neutron turns in, so it'd be you're going to have 33 in the bottom, and 78. So it's going to be a new element, which is AS. How about this one? This will be the last one we're going to do right here. You have 131 over 54. 131 is protons and neutrons, and 54 is the protons. You have Xeon. It says asterisk denotes the nucleus is in very excited state. We'll just say that. So it's very excited. When you have very excited, you're going to have gamma rays. So does gamma rays change anything? No. This whole thing is going to stay exactly the same, but just emit gamma rays. So here we go. Gamma rays. Since gamma rays does not change, the missing particle is simply lower state of energy. So gamma rays right here, the Xeon stays the same, only it's a different state of energy. So, okay, let's stop there.